fundamentals of electrical circuits. In the first subsection, we are moving on to circuit elements and their working. In this subsection, we'll be talking about resistors with their application in incandescent lamps, the inductors minus their application in the electrical machines, and the capacitors minus their application in cables and insulators. So in this session today, we will talk about self and mutual inductances and resistors. So to start off with the theory, in associated theory, there are several laws and principles as also interpretations. So a few of them are put in here such that these interpretations and formulae and equations can be made use of in solving of problems and also for a deeper understanding as to their workings. One of the most important aspect happens to be that all these elements to follow the conservation law are also associated with certain other laws. Like for instance, for the resistor, it is the Ohm's law, and for conversion, the Joule's law becomes applicable. Similarly, Lenz's law is applicable to the inductors, and it can be extended to the capacitors. So the geometric application regarding its size, what all are involved, the materials, content, etc. The geometric interpretation gives a sort of a comparison in the sense that if the resistance of an element is given by rho, it is its material property, multiplied by L, the total length, divided by the area of cross section of the element which has a particular resistance. And then similarly, the inductor, which is a coil around a magnetic material, then it is given by N square, which is the number of turns on the coil, the copper coil or the aluminum coil, whatsoever. Then you have mu naught and mu r, which refers to the total permeability of the medium that is inserted in the coil. Then again, the area of cross section of the iron or where the winding is wound on, and on the length of the iron. If you are talking about a solenoid with an iron core, then the length of the iron. Okay, so here we have two materials working together. One is the copper wire, which has a number of turns as given by N, and we also have the iron piece inserted inside, which has an area for its cross section and its length. Okay, so this is so with the inductance is given by N square mu naught mu r A by L. Similarly, the capacitor has two metal plates separated by a voltage across them, and so it brings all these aspects into the picture by talking about the permittivity of the medium within, epsilon naught and epsilon r taken together, the area of the parallel plates, and d, the distance between them across which the voltage is applied. So this gives a geometric interpretation, and there is a functional interpretation and input-output interpretation, which is all which actually throws light on its working. And we also have the energy storage inside, and some problems in this regard, where the capacitor stores an energy as given by half Cv square, where we use the steady state voltage. Similarly, half Li square for the inductor. Okay, and when you're talking about a pair of inductors, which is a very important application with respect to machines, then two aspects come into the picture. Whether the pair, of course, the pair releases what is called as a mutual inductance also between them, and so the fluxes, the nature of the flux is also getting to be important. There are two possibilities. One is that the two fluxes created by the two coils may be aiding each other, or they may be opposing each other. The next feature that needs to be considered is whether these coils are connected in series or in parallel. If they are connected in series and the fluxes are aiding, then the total inductance gets added together as L1 plus L2 plus 2M. On the other hand, for a series connection with the fluxes opposing, then the total becomes L1 plus L2 minus 2M. These quantities need to be remembered. Similarly, if these inductances, if these coils are connected in parallel and the flux is aiding, and thereafter when the flux is opposing, the numerator remains the same. That is, in the computation, the numerator remains the same, and it had better be remembered as L1 L2 minus m square. But the denominator for the aiding version gives rise to more flux as given by total inductance as given by L1 L2 minus m square divided by L1 plus L2 minus 2m. On the other hand, when the fluxes are opposing each other, the total inductance is actually reduced, because we have L1 L2 minus m square divided by a larger quantity as given by L1 plus L2 plus 2m. So these are important formulae that had better be remembered, and the problems addressed accordingly, because it throws light on the workings of these connected together. Okay, there are other relations also which gives rise to comparison between the electrostatic happenings inside the capacitor and electromagnetic happenings inside a solenoid. Okay, so they are but some of the most, okay, of course they can be, most of them need to be remembered, but another important understanding needs to be that for an inductor, it's important to remember that there is a reluctance to flow of flux, and this reluctance is given by the cause-effect relationship. So what is cause and what is effect? Okay, so there is what is called as a magnetomotive force as given by the number of turns multiplied by the current flowing through the coil, which is giving rise to a flux flowing through the magnetic medium or through air. Okay, so we have Ni by phi is the same as equal to R, and it's a different kind of R written altogether differently, and it is given by similar to rho L by A, but mu being permeability and not resistivity. It has a relationship as given by L by mu A. Okay, so I suppose the rest follows through accordingly, and so let's move to some of the applications with respect to problems. Okay, so the first problem marked here, we are shown a toroid around which two coils are wound. So on observing the primary side, it is seen that primary on the left hand side can be seen that there is a source of V cos omega t and there is a current I sin omega t, and so the relationship tells us that now the source is feeding a pure reactance, okay, and that too an inductive reactance, because the current is lagging the voltage by 90 degrees. Okay, so and what is the effective reactance? It will have its self own inductance and also mutual inductance if it is possible, but in this case there is no mutual inductance because the coil on the right hand side is open circuited, so we have, or the secondary is open circuited, so we have no current flow through there, which if current was flowing, it would have caused a flux and so mutual inductance. So there's no flux and so there's only self-inductance. And what is self-inductance? It is given by the NP square, because NP is the coil winding specific to self-inductance of this coil or the system or this toroid. So we have NP square, then again mu naught mu r A, which is the cross-sectional area of the iron of the core, that is equal to pi small r square as can be seen there, and then again divided by L, which is equal to 2 pi capital R. Okay, that is the total length. So the area and the length refer to the iron as such. Okay, the core as such. Okay, so now we see that from amongst the answers we realize that there has to be a 2 on the denominator, because 2 pi R 2 cannot cancel with anything. Pi of course can be cancelled, and when you are okay, so that's one thing. And then again when you are talking about the length, okay, so now let's read the question. A transformer with toroidal core of permeability mu is shown in the figure, assuming uniform flux density across the circular core cross section of radius r less than r, that is the radius of the core is smaller than its structural radius, which is capital R, okay, and neglecting any leakage flux. Leakage flux will always make it non-linear, so we are so for simplification, always leakage flux is removed, okay, and the best estimate for the mean radius R is, okay, so this is what is required, which means that V by I is equal to NP square mu naught mu r pi r square, which is a, divided by 2 pi r, should give you r as r on the other side, and so you should have 2v on the denominator, and only one answer comes through as correct, that is D. So we'll just check it out, because now if pi and pi from the numerator and denominator cancel, I should go on the numerator, and you should have mu naught mu r or mu on the numerator, and you should have NP square, which is true. You should also have pi r square, of which pi is removed r square, and you should have omega, because it is essentially omega L, which is L effective, which is being compared to V by I, okay. So I suppose that the answer D is correct, is convincing enough for you. And let's move on to the next problem, yeah, which is again of a sort of a core with a rectangular kind of construction. With length shown as equal to 10 plus 10 plus 10 plus 40, almost 40, a little less because there's an air gap as well, and there's only one single coil, okay, through which current enters, and making it all a magnetic kind of, making it a magnet. Okay, so let's read the problem. The magnetic circuit shown below has a uniform cross-sectional area and air gap of 0.2 centimeters. Okay, the mean path length of the core is 40 centimeters. Though it's little lesser, we can take it as 40. Okay, assume the leakage and fringing fluxes are negligible, which means that the nonlinearity is taken care of. It is removed from the situation. Otherwise, we have difficulties in computation. When the core relative permeability is assumed to be infinite, the magnetic flux core relative permeability is assumed to be infinite, means that the iron allows all the fluxes to flow, or in other words, its reluctance is equal to 0. Okay, the magnetic flux density computed in the air gap is 1 Tesla. So everything goes to the air gap. Okay, so that's, and it is equal to 1 Tesla with same ampere turns, that is Ni remains the same. If the core permeability is assumed to be 1000, now mu r became 1000. The flux density in Tesla calculated in the air gap. So now there is two addition to the reluctance. There are two parts to the reluctance. One is the air, what air offers, and what the iron offers, because now it has reduced permeability. It does not have infinite permeability. Okay, so now the cause effect relationship Ni by phi, or which is the same as equal to Ni remains the same. Phi is B into A, or flux density into area, which area also remains the same. It's only the flux density which changes. And in all cases, its reluctance is given by L by mu naught mu A, where in this case we have two separate pieces offering reluctance. One is the core, the other is the air. And in case 1, when the core is not offering any reluctance, K by 1. Everything that remains static is now rolled into K. So K by 1 is 1 Tesla, the flux density in the air when the reluctance of core was equal to 0, is equal to 0 plus 0.2. Okay, so 0.2 is the length. Okay, L by mu naught mu A. A is removed, okay, and mu is also taken to the other side. Okay, so now we have this, when you're talking about the case 2, when there is a different kind of flux density in the air gap because of the core also offering reluctance, K by B is the same as equal to 40. 40 is the length, centimeters. Both are in centimeters. 0.2 is also in centimeters. 40 divided by the new mu r, that is 1000 plus 0.2. Okay, so so now it's a very simple calculation, in the sense that we have B as equal to 0.2 divided by 0.24, which is almost equal to, okay, so it's approximately equal to 0.835. That's enough for these contexts. Okay, so moving on to the third problem. Here we see some capacitive reactance, a resistance, and two inductances connected together in series with a dotted terminal and a mutual inductance between them. A dotted terminal refers to the fact that if current enters the dotted terminal in both the coils, then you are having aided fluxing, okay, aiding of the fluxes. Otherwise, it's going to be opposing. Okay, so we have here such a situation, and let's read the problem. In the circuit shown below, it is found that the input voltage and current are in phase, which means that there is only resistance acting, or the minus J12 gets cancelled with the overall effective inductive reactance. Okay, the coupling coefficient is K equal to M by root L1 L2. So of course K, the maximum value that K can have is equal to 1 if all fluxes between A and created in circuit number 1, the coil number 1 and 2 coupled with each other, then you have having full mutual coupling. Okay, or K equal to 1, where M is the mutual inductance between the two coils, the value of K and the dot polarity of the coil P and Q. Okay, so now we see that for resonance condition, minus J12 is equal to L1 plus L2 plus 2M. So L1 plus L2 is L1 plus L2 plus or minus 2M. So we are having L1 plus L2 as 16. So now it's going to be minus 2M, or opposing fluxes, and that's and so minus 2M is equal to minus 4J minus 4, and so we see that M is equal to 2, and so M by root L1 L2 is equal to 0.25. So either there are two answers, possible answers, A and C, and since the fluxes have to be opposing in nature, the dot has to be on the Q terminal, such that the current in a series circuit enters in the first coil at the dotted and exits from the second coil at the dotted terminals. Okay, so let's move to the problem number 3. Problem number 4. Again, we see a source feeding a resistor and a coupled set of coils, 4 Henry and 5 Henry, and we also have a capacitance on the other end. Let's see what the problem is. In the magnetically coupled circuit shown in the figure, 56% of the total flux emanating from one coil links with the other coil. Okay, the value of the mutual inductance. So all the peripheral details are not required, and we have only 4 Henry and 5 Henry interacting with each other, such that there is mutual inductance. Okay, and that's given by 4 into 5, 20. Its square root multiplied by K. K is equal to 56% is coupling with each other, so 0.56. Okay, so that gives you an answer for the mutual inductance in Henry. On the other hand, if reactance was required, you would have to use omega as is given in the the source as equal to 4, because it is 60 cos 40 plus 30. 30 degrees is irrelevant in this case. Okay, so fifth problem, two identical coupled inductors are connected in series. The measured inductance for the two possible series connections are 380 microhenry and 240 microhenry. Their mutual inductance is microhenry. So the same old problem, we have L1 plus L2 plus 2M as 380 and minus 2M as 240. So if you take the difference between them, you get 4M as equal to 380 minus 240, then divide by 4. That will give you the mutual inductance in microhenry. A simple problem, but such problems also come for gate examinations. Okay, problem number 6. Wherein we see that there is the waveform given with 6 amps. It's a waveform because time is on the horizontal axis. Okay, and two different timings are marked, 2S and 4S, with respect to the origin 0. Okay, so moving on to reading of the problem, shows the waveform of the current passing through an inductor of resistance. So now the inductor is not an ideal one. It's a practical one with 1 ohm resistance and 2 Henry inductance. Okay, the energy absorbed. Energy is asked, so remember the time is going to be of importance. Okay, in the first 4 seconds. So we have now one component wherein we are having the inductor, assuming steady state with 6 amps flowing through it. So we have half Li square. So we have the 36 joules. Okay, half Li square will give you the joules. Okay, now for the resistor, we need to, the resistor is also absorbing. Okay, so in this case it's not energy stored, energy absorbed. So the resistor is also absorbing. It is absorbing steady energy between 2 seconds and 4 seconds. That is for 2 seconds, and the current is 6 amps, and the voltage across it is now going to be all the voltage because the inductor has short circuited. So we have 6 ampere flowing through 1 ohm, so it is 6 volts. So 6 to 36. Okay, 36 into 2, that is 72. Okay, 2 for the time. Okay, so we have now for the inductor, the steady state 36 joules, and for the resistor steady state, it is going to be 72 joules. Okay, now coming to the energy that is expended in the resistor as the current rises to 6 amps through in voltage. Okay, so let's look at the I square RT picture, which is better. Okay, so what is I square RT telling you? We are having a changing current between 0 and 2 seconds, and it's given by the slope that is equal to 6 by 2, which is 3, and then the time is so mx, so at its time, so that is 3t. Okay, and now 3t is going to be 3t has to be squared, so it's going to be 9 t squared. That has to be now integrated between 0 to 2. Okay, so that gives you 24 joules, and together you have 132 joules. Okay, I suppose the methodology is satisfying to you as well, and we move on to problem number 7. Okay, so here we are trying to do more problems in a short span, such that since the concepts are easy, okay, and all the concepts will be outlined together at the end. Okay, so two 2 Henry inductances, identical, are connected in series and are also magnetically coupled to each other. Okay, so there is also L1 plus L2 plus 2M or minus 2M. Okay, to each other, the coefficient of coupling being 0.1. So we now have a value for M as well. The total inductance of the combination can be. So there are two possibilities. One is L1 plus L2 plus 2M, and other is L1 plus L2 minus 2. Okay, so let's look at M. M is going to be 0.1 into square root of 2 square, or so 0.1 into 0.2. Okay, so now 0.1 into 2, which is 0.2, and 2M is going to be 0.4. Okay, so there's going to be an addition to L1 plus L2, or there's going to be a subtraction to L1 plus L2 by this 0.4 Henry, and so answer D comes out as immediately as true. Okay, so not much need, no need at all for doing it on paper. Okay, and we have 4 answers where M and L1 and L2 are connected. No doubt about it. K is at least at the most equal to 1. So M is always going to be less than or equal to L1 L2, square root of L1 L2. Okay, so let's see. Given two inductors L1 L2, the mutual inductance M satisfies. Okay, so the answer D is obviously true. Now we are having two identical coils, each with inductances of L are placed together on the same core. If an overall, so they are either connected in series or in parallel, but they share the same flux. Okay, if an overall inductance of alpha L is obtained by interconnecting these two coils, the minimum value of alpha. Okay, the minimum value can the most be 0. Okay, it cannot be negative. Okay, so we have to see, is there a situation when you are getting what is called as alpha equal to 0. It is possible, since the coils are identical. You can have L1 plus L2 minus 2M, where M can also be L, which is a possibility when K is equal to 1. So the answer is 0 is automatically understood. Okay, problem number 10. Here we come to resistors with their application in lamps. Okay, so the very important point to remember here is that the brightness, the voltage share, everything happens to be with respect to the resistive content in the content expressed as a ratio, etc. in the lamps. Okay, so now when you are talking about a 200 watt by 200 volt incandescent lamp, it is essentially talking about voltage square divided by power as the resistive content. Okay, that is the material content of the lamp. Okay, so that's equal to 200 square by 200. Okay, so that is 200 ohms. Okay, yeah. So now incandescent lamps connected in series would consume the same total power as a single 100 watt, 200 volt incandescent lamp. So what is a 100 watt to 100 volt incandescent lamp? It is a resistance equal to 200 square divided by 100, which is equal to, again now, a 400 ohm resistor. So now for these two resistors to be equivalent, you need 2 of the first one, or in other words, you have to use 2 of them to constitute the same amount of to consume the same amount of power. Okay, yeah. So now we move on to another problem wherein two incandescent light bulbs of 40 watt and 60 watt. Okay, so 40 watt means a particular voltage, let's say V square by 40 gives rise to a larger resistance when compared to V square by 60 watt. Okay, rating. Okay, so if it has a larger voltage, it means that it gives rise to a bigger brightness. Okay, so ratings are connected in series across the mains. Then the bulbs together consume 100 watt. Not possible at all, because now the voltage is being shared, okay, and the larger component is being taken by the 40 watt, okay, and the share is not very clear, though they say that it could be 50. No, it cannot, it need not be, okay. So let's see what the other answers are. The 60 watt bulbs glows to brighter. No. It is the 40 watt bulb which is going to grow brighter, because it has a higher resistance, and so of the potential dividers made by these two lamps in series, the larger portion of the voltage is taken by the 40 watt, okay, and the answer D is automatically right, naturally right. So the 40 watt bulb glows bright, okay. 12th problem. Suppose that resistors R1 and R2 are connected in parallel to give an equivalent resistor R. If series R1 and R2 have tolerance, if the resistors R1 and R2 have tolerance of 1% each, okay, so which means that the tolerance is now at the most equal to 1, okay, when they're connected in parallel, one particular resistor matters, and the smaller resistance is one that matters, okay. The equivalent resistor R for resistors R1 300 ohms and R2 200 ohms will have tolerance of, okay. So now the relationship is given here, you had better remember it, but then it's going to be at the most 1 or a little less than 1, that's all, okay. So it can't be 1.2 or 2, it can't be 0.5, which is too less, okay. So let's see, the relationship is R1 divided by 1 plus R1 by R2. If R1 is equal to 300, then the percentage that is 1% divided by 1 plus 1.2, 300 by 200. And there's another component also which is given by again our percentage is 1%, and then we are having 1 plus R2 by R1, which is equal to 200 by 300. As was mentioned earlier, the lower resistance now brings about a bigger change, and so we see that the answer is near around 1%, okay. The last of the problems, here we have a connection is made consisting of resistance A in series with a parallel combination of B and C. So we have the picture of A emerging connected with B and C in parallel, okay. 3 resistors of value 10 ohm, 5, 2 are provided. Consider all possible permutations of the given resistors into the positions A, B and C. Identify the configuration with maximum possible overall resistance. For addition, the best thing is to have the largest value as a part of it. When addition is series oriented, okay. So we have 10 plus 5 parallel 2 as the best possible maximum resistance releasing configuration, okay. So of the given resistors, identify the configuration with maximum possible overall resistance. So no doubt about it, that's equal to 10 series with 5 and 2 in parallel, so 80 by 7, okay. And also the ones with minimum possible overall configuration resistance. So back to the original idea of 2 plus 5 and 10 in parallel. So we see that it's equal to 60. The combination is equal to 2 plus 5 into 2 by 3. So that's equal to the overall is equal to 16 and 2 by 3. So now the ratio is going to be 80 by 7 divided by 16 by 3. Okay, so very simple. Okay. The last of the problems, we see two strings of resistors. One is 5 ohms, the other is into combination 10 ohms. So if 5 ohms takes I amps, then 6 plus 4, 10 ohms will take I by 2. Okay, so that's automatic. Let's see in the portion of a circuit shown, if the heat generated in 5 ohm resistor is 10 calories, so it is the same in per second, which means that into 1. Okay, so 5 square. I square 5 is equal to I square 5 into 1 is equal to 10 calories, and then and the heat generated by 4 ohm resistor, which means that I square by I by 2 whole square, I square by 4 into 4 is what? Okay, so what is I square? That's essentially what is asked. So that can be easily obtained from I square into 5 is equal to 10. Okay, so it is 2. Okay, so that concludes the almost all the problems that can be associated with this kind of concepts, and the concepts are outlined one after another in the subsequent slides, such that they can be absorbed, because quite a large number of different types of problems were discussed. I hope that the ideas are well absorbed and will be consequently more absorbed as time goes by. Okay?